Hello and welcome to Professor Iyer's online FRM classes. Let's talk about value at risk through Monte Carlo simulations. In this class, you should be able to understand what is the geometric Brownian motion, which is a very key concept in many quantitative finance theories. You will also see an illustration of a Monte Carlo simulation which is based on the GBM. And finally, we will measure the value at risk based on the simulation. So what is the Monte Carlo value at risk? What is the Monte Carlo technique? It is a method to simulate stock prices over a horizon. The horizon may be 1 year, it may be half a year, or any other specific horizon. What's the value at risk? It's the maximum loss that you can incur over the horizon expressed with a confidence level. So you have a 95% value at risk, which means that you're 95% sure that the maximum amount that you could lose on the stock or the portfolio is such and such dollars. And so the Monte Carlo value at risk is, if you simulated 100 prices and arrange them in ascending order, the value at risk would simply be the current price minus the fifth price. 5 by 100 is 5%, so current price minus fifth price is the value at risk. So if this represents the distribution of stock prices over the horizon at the end of the horizon, and if this is the current stock price and this the fifth percentile stock price, then the difference between them is the value at risk. Now that is the value at risk in a formula. It's the current stock price minus the fifth percentile stock price. Let's look at stock price processes to get more idea before getting into the Monte Carlo simulation. One of the key assumptions of stock price processes is that they follow what's called as a Markov property. The Markov property basically implies that the future movements in the stock price depend only on the current stock price and not on the past price history of the stock. So we assume that the stock price follows a Markov property. One type of Markov process is a Wiener process. A Wiener process applies to a variable whose value changes continuously, and the change in a small interval of time delta t is denoted by delta z. Now for a variable to be called a Wiener process variable, it has to fulfill two conditions. The first condition is that the delta z or the changes are equal to epsilon into root of delta t. Now epsilon here is simply a randomly picked up z value from a standard normal distribution having mean 0 and standard deviation 1. The second condition that it should fulfill is that the changes delta z for any 2 points of time are independent, which means the change at one point of time does not depend on the change at any other point of time. Now if a random variable follows these two conditions, then it is a Wiener process. So what are the properties of Wiener process? The diagram here shows a Wiener process here. So if this time t on the x-axis is divided into smaller intervals of size delta t, then if we take the mean of the changes in z, that is the dz's in each of these intervals, the mean of that should be equal to 0, which means, in other words, the mean of zt minus z0 is equal to 0. That's the first property. The second property is that the variance of zt minus z0 is equal to t, which means that the variance of a Wiener process is simply the amount of time that has passed from time t is equal to 0 to t is equal to capital T. In other words, we are saying that the standard deviation of zt minus z0 is equal to root of t. So let's look at a Wiener process in a diagram. If the y-axis here is z, the Wiener variable, and t is time, this is one example of the Wiener process. So what is a generalized Wiener process? A generalized Wiener process has two additional terms. By the way, the generalized Wiener process is also known by another term called the arithmetic Brownian motion. So this is the equation representing a generalized Wiener process. Here delta z is equal to a into delta t plus b into epsilon into root delta t. Now notice that there are two additional terms here, a and b. What do these terms imply? We will very soon see. Now the mean change in z in time delta t is a into delta t, which means a here is the growth rate or the drift rate of the process. It is the rate at which the variable z increases with time. So in time delta t, a into delta t will be the mean change. What is b here? B represents the volatility. So the standard deviation of change in z in time delta t is equal to b into root of delta t. So a is the deterministic term, b is the random or stochastic term. So the Wiener process has two of these terms, a and b, the deterministic and the random term. Now note that if a is equal to 0 and b is equal to 1 in this equation, the equation will reduce to a Wiener equation. Let's look at the generalized Wiener process in a diagram. On the y-axis we have z and on the x-axis we have t. Now the green line here represents the drift rate of the process, and the slope of this green line is what the term a stands for. Now here is our generalized Wiener process. The process is growing at the drift rate, but it is not equal to the green line because there is also a volatility term b. If b were equal to 0, then the generalized Wiener process will be the same as the green line, but that's not the case here. The value of b is not equal to 0, and so we have the black line. Now let's look at what is the Ito process for stock price. Again, a very key idea in quantitative finance theories. In continuous time, it is represented by this differential equation: ds by s is equal to mu dt plus sigma dz. Now this is also known by the familiar name geometric Brownian motion. We could also write this equation as ds is equal to mu s dt plus sigma s dz. We have only taken the s on the denominator of the left side and taken it to the numerator on the right side. Now dz we know from the Wiener equation is epsilon into root of dt, where epsilon is a z value from a standard normal distribution with mean 0 and standard deviation 1. Now what this process is talking about is this ds by s, and it's saying that it is a function of two things, mu and sigma. So what is mu? Mu represents the expected return of the stock and sigma represents the volatility. So the Ito process is basically a function of these two terms, the expected return and the volatility, or the deterministic and the stochastic term. In discrete time, the equation is given by delta s is equal to mu s delta t plus sigma s epsilon into root of delta t. The equation is exactly the same as the continuous time, the only difference being that we don't say ds, we instead say delta s. Similarly, we don't say dt, we say delta t. That's the only difference. So here we have the stock price equation. What is the stock price for time t plus delta t? It is equal to the stock price at time t, st, plus the change in the stock price, delta s. So here we have a method of generating the stock price for many points of time, and we can generate many stock price paths. Because we have a random term here, we can generate many stock price paths, and that is what we are going to use to do the Monte Carlo simulation. This is the equation that is of relevance to us for our value at risk calculation. Now the Monte Carlo simulation boils down to saying that if the current stock price is $50 and the mean return is 10% and the standard deviation is 20%, At the end of 1 year, the stock return will have a probability distribution of n 10, 20, where n mu comma sigma is a normal distribution with mean mu and standard deviation sigma. So the Monte Carlo simulation is basically going to allow us to simulate values from these parameters mu and sigma, so that we are going to get many stock prices. The key thing to remember is that we are going to divide the time capital T into many steps, small discrete steps, each of size delta t, and we are going to generate many paths. So here we are taking t steps and n paths. So let's go to Microsoft Excel and actually try out a simulation and see how it looks like. So here is my spreadsheet, and I'm going to take these parameters, time as half a year divided into 50 time steps, and I'm going to take 20 stock price paths. I'm not going to take a higher number because that might make the chart look a bit cluttered, so I want to avoid that. And then I'm going to take the initial price as 100, the expected return mu as 5%, and the volatility sigma as 40%. Now before I click on simulate, I'll just show you that the simulation is basically going to come out of a VBA macro, which is here. Although we can do the simulation even without a VBA macro, we can do it in plain Excel itself because we know the differential equation, we can do it. But to make it easier, I have done this. I'm going to click on simulate and see what happens. There we go. What we have here is 20 geometric Brownian motion paths, which means 20 stock prices. Now note that every stock price is starting with a value 100. Right now, over 50 time steps, each of these 20 stock prices have evolved differently. Now what is of concern to us, what is of interest to us, is only the stock price at the end of this horizon, which is what we are going to use for our value at risk calculation. In this case, we see that the pink or magenta color stock price is the stock price having the least value at the end of the horizon, and that is of importance to us because if we arrange the 20 stock prices in ascending order, this is the least one, and so our value at risk is going to be 100 minus the value of this pink color stock price at the end of the horizon. So let's get back to our value at risk. We defined it as the maximum dollar loss over a horizon expressed at a confidence level. Now from the simulation, if we sorted prices in the ascending order, imagine we simulated 20,000 stock prices, and then 5% of 20,000 is 1,000, the current stock price minus the 1,000th stock price, assuming that we arrange the stock prices in ascending order. Again, to re-emphasize in a diagram, if this is the current stock price and this the 5th percentile stock price, the difference between them is the value at risk. The current stock price minus the 5th percentile stock price. That's all in this presentation. If there are any questions, I'll be glad to take them. Thank you for watching this video.